A warm welcome to all. This is Aishwarya from AINDS from Johnson's Institute of Technology. Today, my topic is Schrodinger wave equation. Schrodinger wave equation is a linear partial equation that governs the wave function of a quantum mechanical system. The Schrodinger equation gives the evolution over time of a wave function, the quantum mechanical characterization of an isolated physical system. It is the derivative of Schrodinger wave equation. It divides into two types of wave equations. They are time dependent wave equation and time independent wave equation. Schrodinger time dependent wave equation is a partial linear differential equation that describes the state function or wave function of a quantum mechanics system. It is a very important result in quantum mechanics or modern physics. This equation, presented by Erwin Schrödinger in 1925 and published in 1926. It is the derivation of a time dependent wave equation. Consider a particle of mass m with velocity v and under the influence of potential energy, which is represented by v, the total energy of a particle system. These are the derivatives of Schrödinger wave function. Schrödinger equation is the name of the basic non-relativistic wave equation used in one version of quantum mechanics to describe the behavior of a particle in a field of force. There is the time-dependent equation used for describing progressive waves applicable to the motion of free particles. Assume that we can factorize the solution between time and space. Equation is often called the time-independent Schrödinger equation. This is the derivation of time-independent wave equation. Consider a particle of mass m moving with velocity v in space. Suppose a system of stationary waves is associated with the particles at any point in space in the neighborhood of a particle. Examples of Schrödinger wave equation: curvature of wave functions. Schrödinger's equation in the form is given here. For a constant potential, the wave function is phi of x equals to ax plus be minus ax. Of course, this wave function will diverge in at least one direction. However, as we shall see below, there are situations with spatially varying potentials where this wave function is only relevant for positive x and the coefficients a, b are functions of the energy. For certain energies, it turns out that a equals to 0 and the wave function converges. Let us discuss about the parity of a wave function. We call the operator that reflects a function in the origin the parity operator p. So, these eigenstates of the Hamiltonian are also eigenstates of the parity operator with eigenvalues plus or minus 1. This is because the Hamiltonian is itself symmetric and the two operators can be simultaneously diagonalized, that is, a common set of eigenstates can be constructed. This is about the Schrodinger wave equation. Thank you all.